In this question, you can see that there is a cylinder whose inner radius is r, and there is a cork which is to be fitted into the cylinder, and the length of the cork is L, and its radius is 2 into radius is r plus delta r. Now this cork is also in cylindrical shape, and we need to fit this cork into the cylinder. So we need to apply some pressure, and we need to compress this cork, and then we need to fit it in the cylinder. So we are required to find out this extra pressure which we should apply on the cork so that it can be fitted into cylinder. So first of all, we know that cork is of cylindrical shape, and the area of cylinder, the surface area of cylinder, is curved surface area, in fact, because we are applying this force on the curved surface. So we need to take curved surface area, and curved surface area of cylinder is pi 2 pi RL, and volume, curved surface volume, in fact volume of cylinder is pi r square into L. Now dV will be pi into 2r dr into L, and dV upon V will be equal to pi into 2r dr into L by pi r square into L. Okay, so cancelling out this, we get dV by V equal to dr by r, and this is 2 dr by r. Now we know that strain developed is dV by V, and therefore strain in this cork will be 2 dr by r. So the stress which we need to apply will be strain into bulk modulus. Now the bulk modulus of this cork is given as beta. So the stress, which is delta P, which we need to apply on this cork, will be 2 dr by r into bulk modulus. So this is the required value of delta P, 2 dr by r into bulk modulus. Now in the second case, it is given that after cork is fitted into this cylinder, then how much force is needed to pull it out of the container if the coefficient of friction between container and cork is mu. So it is very simple to understand that if this cork is fitted into the cylinder, then the length of the cork is L, and the friction would be acting on the surface, curved surface of the cork. And this friction, the force which we need to apply on this cork to pull it out, will be exactly equal to F, or we can say that this force is slightly greater than friction. So friction would be equal to mu into normal reaction. The normal reaction which is applicable on this cork. This normal reaction is delta P into area, because delta P is the pressure, and the force which the cork is applying on the glass, or glass is applying on the cork, is P into area, and area is the curved surface area of the cork. So delta P into area is 2 pi RL. This is the normal reaction, and we have already derived the value of delta P, which is 2 dr by r into beta. So this is 2 dr by r into beta into 2 pi RL. This is the normal reaction, and the friction required is equal to mu times of normal reaction. Therefore it is 4 beta dr into pi into L, and I have cancelled this R with R. So this is 4 beta dr into pi into L. Now we move on the next question. In this question, you can see that it is given that if we suspend a load of mass m from a wire, then it produces a strain of 1%, and this strain is sufficient to break the wire. So first of all, the breaking strain produced in the wire is 1%, which means that change in length upon original length is 10 to the power minus 2. Okay, so this is the relationship between the extension upon original length. Now it is also mentioned in the question that now if we have to assume that Hooke's law is valid till the moment the wire breaks, and it is given that there is a load of mass m which is suspended with a wire like that, and wire has a total length of lambda. Now this load is raised to a height of h, and then it is released from this point. So if load is raised to this height, then at this point, till this point, this rope will be slacked, and at the instant when this mass will cross this point, then let's suppose finally it has extended by a small length of x, which is the length at which it would break. So now we can see that this mass has declined by a total distance of h plus x. So we can say that first of all, this is strain, and you can say that strain stress developed in the wire is mg by A, where mg was the load which is required to break this wire, and this is equal to strain, which is 10 to the power minus 2 into Young's modulus. So we can conclude that this Young's modulus of the wire is equal to 100 mg by A. Now you can see that this wire has declined by a distance of h plus x in the second case. Therefore, work done by mg will be mg h plus x. And this work done is used in the form of potential energy stored in the wire, which is half kx square. So this is mg h plus x is equal to 10 raised to power minus 2 into L, and L is equal to lambda in this case, and this is half. K is equal to, now let us calculate K. K is gamma A by L, and gamma is equal to 100 mg by A, and this is A by L, original length is lambda. So cancelling this, so K is equal to 100 mg by lambda. So this is 100 mg by lambda into x square. Now again x is equal to 10 to the power minus 2 lambda, so it would be multiplied by 10 to the power minus 4 lambda square. Now I am writing it on the next page. Now equation is mg into h plus 10 raised to power minus 2 lambda is equal to half mg into, I am cancelling this lambda with lambda, and this 10 raised to power 2 with 10 raised to power minus 4, and it would be 10 raised to power minus 2, and there would be a lambda in this case. So cancelling this g with g, so h plus 10 raised to power minus 2 lambda is equal to half m by m into 10 raised to power minus 2 lambda. So h will be equal to 10 raised to power minus 2 lambda is common, m by 2m minus 1. So this is the required height till which we should raise the load so that when it falls, it breaks the wire. Now let's move on the next question. In this question, it is given that the atmospheric pressure is P naught and the density of the water on the surface is rho naught. We have to find out the pressure deep inside the sea at a depth h, and the bulk modulus is given as beta. Now you must be wondering that this is a very simple question, that pressure inside a depth of h inside a fluid is P naught plus h rho g. But there is a twist in this question. The twist is the fact that as we will descend in the water in the deep of the sea, then the density will also change due to the effect of pressure, because pressure will compress the water also. So the density cannot be constant throughout. So in this case, we can see that pressure density into volume is mass of the water, and it is constant. Mass will not change with the depth for a unit element. So we can say that rho into V is constant. So we can say that rho dV plus V d rho is 0. So rho dV is equal to minus V d rho, and therefore d rho by rho is equal to minus dV by V. This is the first equation. Now we know that the now we know that the stress is equal to strain into bulk modulus, and we all know that stress is dP, strain is minus dV by V, and bulk modulus is beta. So dP here will be equal to we are substituting the value of d minus dV by V, so it would be d rho by rho into beta. This is dP, change in pressure. Now if we integrate dP, now dP is equal to d rho upon rho into bulk modulus. Now if we integrate both sides, and we can apply the limit by using the fact that on the surface of the water the pressure is P naught, and below the water surface at a depth of h, let's suppose the pressure is P, and the density at that point, let's suppose it is rho, and on the surface density is given as rho naught. So P minus P naught is equal to bulk modulus into ln rho by rho naught. And therefore we can say that P is equal to P naught plus bulk modulus into ln rho by rho naught. Now this is the equation number 1. Now there are two variables. In fact, there rho is also a variable. So we need to eliminate this rho, and we need to write the term of h. We know that as we go down, then dP, pressure changes due to height also, and therefore dP is equal to h rho g, and therefore we can write it as dh rho g. Okay, so in this case you can see that dP is also equal to, from equation number 2, this is equation number 3. So dP is equal to d rho by rho into bulk modulus is equal to dh into rho g. So you can see that d rho by rho square into bulk modulus is equal to dh into g. Integrating again, the limit is from rho naught to rho, and here the limit will be from 0 to h. Okay, so h is measured from the surface, as h is the depth of the depth in the water surface. So integration of 1 by rho square will be minus 1 by rho, and limit would be from rho naught to rho and into beta is equal to hg. So you can see that 1 by rho naught minus 1 by rho is equal to hg by beta. This is 1 by rho. Because I have utilized this minus and I have inverted the limits. So this is 1 by rho is equal to 1 by rho naught minus hg by beta. So I can say that rho naught by rho is equal to 1 minus hg rho naught by bulk modulus. Okay, now we can use this fact in the equation this. So we can say that P will be equal to P naught plus bulk modulus into ln. Now you can see that it is rho by rho naught and it is rho naught by rho. So we can invert and we can write it as minus, and if we take a minus common then it would become rho naught by rho. So substituting the value of rho naught by rho, which is 1 minus h g rho naught by bulk modulus. So this is the pressure at a height h below the water surface in the sea. Now we move on the next question. In this question, there is a metal cylinder of length L and radius r, and it is rigidly fixed to the ground, which means that the surface of this cylinder, which is touching the ground, is held fixed. Now this cylinder is twisted by applying a torque of tau naught slowly, and this torque is applied by the some force which is applied along the circumference on the top circumference. The angle of twist is theta naught, and we have to find out the shear modulus of elasticity. Now you have to imagine this question, that we are observing this cylinder from the top. So the cross-sectional view would be like that. This is the cylinder. Now let us assume that this is let us assume a elemental ring inside this cylinder cross-section, and this ring would be extending to the bottom of the cylinder. So this will be a hollow cylinder, but it is ring as we are watching it from the cross-sectional. Now let us mark a point B on the ring. Now when we will twist this cylinder, let us twist this cylinder by angle theta naught. And let us draw the elemental ring again. Now this is the elemental ring. And you can see that after twist theta naught, twisting by theta naught, this mark which we have already made on the elemental ring has moved by a distance by an angle of theta naught. Okay, this you can imagine. So the distance moved by this mark, this one, this is B dash, and this was the initial point B. So this B dash will be equal to r theta. And therefore we can say the strain developed. So strain in this case would be the distance moved by this point upon the length L. You can imagine it with this diagram, that in this case, when this rectangular block is deformed, then strain which we use is this x upon L. So the x in this case is r theta and the length is L. So strain is r theta naught by L. This is the strain. And stress developed at this point will be neta modulus of rigidity into strain, which is r theta naught by L. So stress is force per unit area. And therefore, we can say that torque per unit area will be equal to stress into the radius r, because stress is force per unit area and force into r is torque. So torque per unit area dA is equal to stress, which is n r theta naught by L into r. Okay, so torque upon dA will be equal to neta r square theta naught by L, and the elemental area of this ring element will be 2 pi r dr. So the total torque will be integration neta into r square into theta naught by L into 2 pi r dr. Limit of r would be from 0 to capital R. Now you can see that total torque is equal to tau naught, which we have applied because this cylinder is twisted very slowly. So neta theta naught pi into 2 divided by L. I am taking out all the constants, which is neta theta naught 2 pi by L, and inside the integration it is r cube dr. The limit of r would be from 0 to r, and therefore the expression will be tau naught equal to 2 neta theta naught pi by L. 2 neta theta naught pi by L, and this is r to the power 4 by 4. Limit is from 0 to r. So tau naught is equal to 2 neta theta naught pi by L, and it is 4L and r ki power 4. So tau naught is equal to neta theta naught pi r ki power 4 by 2L. Okay, so neta will be equal to 2L tau divided by theta naught into pi into r to the power 4. So this will be the value of modulus of rigidity. Now we move on the next question. In this question, we have to find out the elongation in this block, and it is given that the mass of the block is m, its area of cross section is a, and gamma is its Young's modulus. So this block is being dragged on the frictionless floor with the force F. So we have to find out the elongation in the block. Now you can obviously see that acceleration of this block will be F by m. Okay, and there is no friction. Now if we find out the tension in the block at some point, let's suppose this point is at a distance of x from this end, and this is L minus x. So the tension at this point will be M1A, where M1 is the mass of this part, this one, and M2 is the mass of this one. And M1 plus M2 is obviously equal to M. So T will be equal to M1A, and M1 will be equal to mass per unit length of the block. into this length of the block, which is L minus X. So into A. So T will be equal to MA into L minus X by L. And we can see that MA is equal to F. Let us use this M as capital M. So MA is equal to A, MA is equal to F. So tension will be F into L minus X by L. Now at this point, let us assume a strip of length dx, original length dx. Now due to this tension, the elongation developed in this strip is dy. So the new length of the strip will be dx plus dy. So the strain produced in the strip will be equal to dy by dx. Now we know that stress is tension upon area. So stress which is T by A is equal to strain which is dy by dx into Young's modulus gamma. Now T is equal to F into L, in fact F into 1 minus X by L, and that is equal to dy by dx into gamma into A. So let us use the next page. So F into 1 minus X by L into dx is equal to dy into gamma A. And if we integrate both the sides, we can see that the limit of x would be from 0 to L, and limit of dy, which is the extension in the small elemental length. So the total extension will be delta L. So F into x minus x square by 2L, limit will be from 0 to L, is equal to gamma A into delta L. So this is F into L minus L by 2 gamma is equal to gamma A into delta L. So delta L, which is the extension in this rod, will be equal to FL by 2 gamma A. So this is the extension which is required to be calculated in this question. Now we move on the next question. In this question, you can see that there is a rod which is pulled with a constant force F in the upward direction. The mass of the rod is m and acceleration due to gravity is g. The length of the rod, natural length of the rod is L, and gamma is its Young's modulus, and area of cross section of the rod is A. We need to find out the extension produced in this rod. Now we know that the acceleration of the rod will be A, and A will be equal to F minus mg by m. So this is A. And let us find out the tension produced in the rod at a distance of x. So let us suppose x is from the bottom end, and the tension at this point T will be equal to, let us draw the free body diagram of this end. So now you can see that the mass of this end is m dash. So m dash g will be acting in the downward direction. Tension will be acting in the upward direction, and this is moving upward with the same acceleration A. So T minus m dash g will be equal to m dash A, and T will be equal to m dash A plus m dash g. So T will be equal to m dash A plus g. Now you can see that m dash will be equal to m by L into x, and A is the acceleration, which is F minus mg by m plus g. Okay, so you can see that T will be equal to mx by L into, this is F by m and this is it. So it would be equal to, T would be equal to Fx by L. Now the stress developed at this point will be Fx by L into A, and this will be equal to the strain, which is dy by dx, which we have already discussed in the previous questions. So you can see that dy will be equal to Fx dx divided by L A gamma, integrating from 0 to delta L and from 0 to L. Delta L will be equal to F L by 2A gamma. So the correct answer will be option number A. Now we move on the next question. In this question, it is given that there is a uniform rod of Young's modulus gamma, density rho, its total length is L, and its area of cross section is A. It is rotated about this axis with an angular velocity of omega. Now we have to find out the correct option, and in all of these four options, two facts are examined. The first fact is the thing that we have to find out the total elongation in this rod, and other one is the elongation per unit length at point O. Now first of all, let us find out the total elongation. We have already discussed in the previous part 1 video, part 1 of JEE Advanced and Nsep video, that the rod, when it is rotating with an angular velocity of omega, the length of the rod is L, then the total extension produced in this rod is rho omega square L cube by 3 gamma. We have already derived this result, so we'll use this result in this question. So you can see that on this half part of the rod, the length is L by 2. So the elongation developed in this half part will be equal to rho omega square into L cube, where L is L by 2. So this is L cube by 8, and 3 into 8 is 24 gamma. So the total elongation, delta L total on the rod, will be twice of delta L of each half part. So the total elongation produced in the rod will be equal to rho omega square L cube by 12 gamma. So the correct option is A, 1. Now in the second part, it is being asked that we have to find out the elongation per unit length at point O. Now elongation per unit length is equal to strain, obviously. Elongation per unit length is strain, and strain is equal to stress upon gamma. Now in the simple words, we are asked the stress at this point divided by gamma. So let us first of all see that if the rod is rotating about central axis, then this part, only this part, will be applying a centrifugal force, which is ml omega square. The m of this part is m by 2. The distance of center of mass of this part from this is L by 4 and omega square. We can concentrate the centrifugal force at center of mass. So this is the pulling force, and the same pulling force will be applicable on this side. So the tension will be developed in the rod at the center. So this T will be balancing this one, and this T will be balancing this one. So stress will be equal to T upon A, where T is ml omega square by 8 and A is the area. So strain, which is the elongation per unit length, is equal to stress upon gamma. So this is m. Now m is the mass of the rod, which is its area into length into density, and divided by 8a gamma. Cancelling this a with a. So you can see that strain will be equal to rho L square omega square by 8 gamma. So the correct option will be option number 4th. Now we move on the next question. In this question, you can see that there is a rod of length L and density rho, and the cross section area of the rod is A. This rod is made up of a material whose Young's modulus is gamma, and it is being pulled from both ends with different forces. The space is gravity free space, and we have to find out the elastic potential energy stored in the rod as well as elongation in the rod. So first of all, let us find out the acceleration of the rod, and we can see that the acceleration of the rod will be net external force, which is F0 divided by its mass m. So this would be the acceleration of the rod. Now let us see that in this rod, let us draw the rod like that. Now in this rod, let us suppose a point which is at a distance of x from this end, and this force is F0 and this one is 2F0. So at this point, the tension in the rod can be calculated by the equation that T, this rod is accelerating in this direction like that. Therefore, this tension T would be pulling this mass in forward direction with acceleration A. So T minus F0 is equal to ma, and let's suppose its mass is m dash and acceleration is A. So T minus F0 is equal to m dash, and m dash is equal to m by L into x, and the acceleration is F0 by m. Cancelling this m with m, T is equal to F0 1 plus x by L. This is the tension developed in the rod at this point. Now the stress developed, let us denote stress with sigma. So stress would be tension upon area. So it is F0 upon area into 1 plus x by L. This is the stress developed in the rod at this point. Now we can see that elongation produced in the rod is again we use the older method in which we always write stress is equal to strain, which is dy by dx, assuming the fact that the original length of some element, let's suppose there is an element whose width is dx and its original length is dx, and the extension due to this tension in this element is dy. So dy by dx would be the strain developed. So let us substitute the value of sigma, which is F0 by area into 1 plus x by L, and that sigma is equal to dy by dx into gamma, where gamma is the Young's modulus. Okay, so dy is equal to F0 by A into 1 plus x by L into dx divided by gamma. Gamma is the Young's modulus. So integrating this from 0 to delta L and this from 0 to L. So delta L is equal to F0 by A gamma, and this becomes x plus x square by 2L. The limit is from 0 to L. So delta L becomes F0 by A gamma, and this is L, and this is again plus L by 2. So you can see that the elongation in this rod will be F0 into 3L by 2 A gamma. So the correct option, one of the correct option is third. Now let us find out the elastic potential energy stored in the rod. For this, we again draw the diagram of the rod. and at this point, which is at a distance of x from this end, we can see that the tension developed at this point is T. And let us again imagine an element of width dx. So we know that the energy density is equal to half stress into strain. Now if we write down the strain as strain equal to stress upon gamma, so it would be stress whole square upon gamma. Okay, so the stress at this point was sigma, which we have already calculated, which is F naught by A into 1 plus x by L. So this is F naught square by A square into 1 plus x square by L square plus 2x by L. Okay, so this is the stress energy density. Okay, now we know that the total energy stored in the wire would be half gamma and F naught square by A square into, this is 1 plus x square by L square plus 2x by L into dx, and integrating both the sides into, in fact, when we this energy density is du by volume du by dv, where dv will be dx into area. So we are taking this dx into a in the upward side. So cancelling this a with a, this becomes half. First of all, F naught square is common, half is common, gamma is common, and a is common. And here it would be x plus x cube by L square, 3L square, plus x square by L. And limit would be from 0 to L. So u would be F naught square by 2a gamma, and this is L plus L by 3 plus L by, this is L. So you can see that it is equal to 7L by 3. So u will be equal to 7 F naught square L by 6a gamma. So the energy stored in this wire will be 7 F naught square L by 6a gamma. So the another correct option will be option number 2. Okay, now we move on the next question. In this question, there is a lift which is ascending in the upward direction with an acceleration equal to g. And there is a wire or a rod, we can say that there is a rod of cross section area A and length L and mass m. It is suspended from the ceiling of this lift. This lift is accelerating in the upward direction, and due to the pseudo force and the mg acting on this wire, it would be expanding. So we have to find out the elongation as well as the elastic potential energy stored in the wire. So first of all, let us see that we have already studied in one of the video in the playlist of elasticity that when a wire is expanded due to its own weight, then we can use an analogy that we can replace the wire, heavy wire, with a massless wire, and we can replace this wire with a mass of m by 2, which is connected at the bottom of the light wire. So we have already discussed this analogy in that video. You can refer that video, and by this analogy I can say that the total of m by 2g, which is mg, plus m by 2a, which is also mg, pseudo force will be acting on this wire. So total tension in this wire will be mg, and therefore the stress developed in the wire will be T by area. So it would be mg by area, and strain developed will be delta L by L, and strain will be stress upon gamma. So it is mg by A and it is gamma. So delta L will be equal to mg by A gamma into L. This is the total length elongation developed in the wire. So the one of the correct answer is option number 1. Now to find out the spring potential energy, we know that this wire is, we are just using this analogy for finding out the elongation. This is not valid for spring analogy. So to find out this, in fact, this is not valid for energy calculations. So to find out the energy stored in the wire, we must use the conventional method. And by that conventional method, we can say that the tension developed in this wire at some point here would be balancing m dash g plus a. Okay, let's suppose this is at a height of x. So T will be equal to m dash, where m dash will be m by l into x into g plus a is 2g, because a is also equal to g. So T will be equal to 2mgx by l. This is the tension somewhere at this point in this wire. And therefore the stress at this point would be T by area. Okay. So T upon area will be equal to 2mgx upon LA. At this point, stress developed. And we know that the energy per unit volume is equal to half stress square, which is 4 mg square into x square by L square A square into gamma, in fact divided by gamma, Young's moduli. And dV is the elemental volume. So elemental volume of an element whose width is dx, let's suppose there is an element whose width is dx, so its volume would be equal to a dx. So the du will be equal to 2 mg whole square x square into a dx. So I'm cancelling out a with a, so it is dx divided by L square a into gamma. And therefore integrating this will be total energy U. So it is 2 mg whole square divided by L square a gamma, L square a gamma, and integration of x square is x cube by 3. Limit will be from 0 to L. So you can see that there would be a term 2 by 3 in this, and hence we can directly point out the answer, which is correct answer, which is option number 3. So the correct answers are 1 and 3. Now we move on the next question.